Welcome to this educational video on the power at infinity limit. Today we're exploring one of the most fundamental concepts in calculus and mathematical analysis. We'll be studying what happens to the function 1 over x to the n when x approaches infinity, where n is any positive number. To understand this concept visually, imagine a graph where x represents increasingly large numbers and y represents the value of 1 over x to the n. As x gets larger and larger, approaching infinity, the value of 1 over x to the n gets smaller and smaller, approaching 0. This concept appears everywhere in science and engineering. In physics, it describes how gravitational force weakens with distance. In engineering, it models how signal strength decays. In economics, it helps understand market behaviors. In this video, we'll break down this concept step by step, explore the mathematical foundation, work through detailed examples, and see real-world applications. By the end, you'll have a solid understanding of how and why this limit works. Now, we're ready to dive into the heart of our topic. This limit formula tells us something remarkable about what happens when we divide 1 by increasingly large numbers raised to a positive power. Let's break this down piece by piece. The expression x approaches infinity means we're considering what happens as x becomes arbitrarily large, larger than any number you can imagine. The expression 1 over x to the n represents our function. As x gets larger and larger, we're dividing the number 1 by increasingly massive values raised to the power n. Now let's see this concept in action with some concrete numbers. I'll show you what happens when we calculate 1 over x squared for increasingly large values of x. When x equals 10, 1 over x squared equals 1 over 100, which is 0.01. Already we can see the result is getting quite small. When x equals 100, we get 1 over 10,000, which is 0.0001. Notice how much smaller this value has become. When x equals 1,000, we get 1 over 1 million, which is 0.00001. The pattern is clear. As x grows, our result shrinks dramatically. And when x equals 10,000, we get 1 over 100 million, which is 0.0000001. These numbers are becoming incredibly tiny. Here's the crucial insight. As x approaches infinity, the value of 1 over x to the n gets arbitrarily close to 0. But notice something important. It never actually equals 0. Think of it this way. Imagine you're dividing a pizza into more and more pieces. If you divide it into 10 pieces, each piece is 1/10. If you divide it into 100 pieces, each piece is 1/100th. As you create more and more pieces, each individual piece becomes smaller and smaller, approaching 0 size, but never completely disappearing. The mathematical term for this behavior is that the function has a horizontal asymptote at y equals 0. The graph of 1 over x to the n gets closer and closer to the x-axis, but never touches it. This concept is fundamental to understanding many areas of mathematics and science. Whether we're looking at the intensity of light as it travels farther from its source, or the gravitational force between objects as they move apart, this limiting behavior appears everywhere in the natural world. Now we need to establish the rigorous mathematical foundation for this limit. While our intuitive understanding is helpful, mathematics requires formal proof to be completely certain of our results. The formal definition uses what we call the epsilon-delta approach. For any small positive number epsilon, we must be able to find a large number m, such that when x is greater than m, the function value is within epsilon of 0. Let me explain what these symbols mean. Epsilon represents any arbitrarily small positive number we choose. M represents a large threshold value that we will construct based on epsilon. Now let's construct the proof step by step. We start by assuming we are given any positive epsilon value. This represents how close we want our function to be to 0. Step 2 is the key insight. We choose m to equal 1 over epsilon, raised to the power of 1 over n. This specific choice is what makes the proof work. Step 3, we assume that x is greater than our chosen m value. This is the condition we need to verify leads to our desired conclusion. Step 4, we raise both sides of the inequality to the power n. Since n is positive, the inequality direction remains the same. Step 5, we simplify the right side. When we raise 1 over epsilon to the 1 over n power, and then raise that result to the n power, the exponents multiply to give us simply 1 over epsilon. Step 6. We take the reciprocal of both sides. When we take reciprocals of a positive inequality, we must flip the inequality sign. This gives us exactly what we need. Step 7. Since 1 over x to the n is always positive, the absolute value of 1 over x to the n minus 0 is simply 1 over x to the n. Therefore, we have proven that this is less than epsilon. This completes our proof. We have rigorously demonstrated that for any epsilon greater than 0, we can find an m such that when x is greater than m, 1 over x to the n is within epsilon of 0. This confirms our limit equals 0. What we have proven is that given any arbitrarily small positive epsilon, we can make 1 over x to the n arbitrarily close to 0 by choosing x sufficiently large. This is the precise mathematical meaning of our limit. The exponent n plays a critical role in determining how quickly the function 1 over x to the n approaches 0 as x approaches infinity. Understanding this rate of convergence is essential for grasping the behavior of these power functions. Rate of convergence measures how quickly a function approaches its limit value. For 1 over x to the n approaching 0, larger values of n make the function approach 0 much faster. Let's compare 3 different cases, n equals 1, n equals 2, and n equals 3. We'll examine how the functions 1 over x squared, and 1 over x cubed behave differently. Now let's look at actual numerical values to see the dramatic differences in convergence rates. We'll evaluate each function at x equals 10, 100, 1000, and 1000. At x equals 10, notice that 1 over x gives us 0.1, 1 over x squared gives us 0.01, and 1 over x cubed gives us 0.001. Already we see the dramatic difference. At x equals 100, 1 over x is 0.01, 1 over x squared is 0.0001, and 1 over x cubed is 0.0001. The gap is widening significantly. At x equals 1000, 1 over x is 0.001, but 1 over x squared is already 0.00001, and 1 over x cubed is 0.000001. The higher powers are approaching 0 much faster. At x equals 1000, the pattern becomes even more dramatic. While 1 over x is still 0.001, 1 over x cubed is practically 0 at 0.000001. Why does this happen? When we increase the exponent n, we're dividing 1 by x, multiplied by itself n times. This means we're dividing by a much larger number, so the result gets smaller much faster. We can categorize these different rates of convergence. When n equals 1, we have linear decay, which is relatively slow. When n equals 2, we have quadratic decay, which is much faster. For n equals 3 and higher, we have polynomial decay that becomes increasingly rapid. The case where n equals 2 is particularly important in physics. We see quadratic decay in gravitational force, light intensity, and electric fields. These are called inverse square laws, and they govern many fundamental physical phenomena. The key takeaway is that the exponent n controls the speed at which 1 over x to the n approaches 0. The larger the value of n, the faster the convergence to 0. This fundamental concept helps us understand the behavior of power functions and their applications across mathematics and science. Now we'll examine our first concrete example, the limit of 1 over x as x approaches infinity. This is the simplest case where n equals 1. To understand this limit, we'll examine what happens to 1 over x as we substitute increasingly large values for x. This numerical approach will help us see the pattern clearly. When x equals 1, 1 over x equals 1. When x equals 10, 1 over x equals 0.1. As x becomes 100, 1 over x becomes 0.01. Continuing this pattern, when x is 1000, 1 over x is 0.001. When x reaches 10,000, 1 over x becomes 0.0001. And when x is 100,000, 1 over x is just 0.0001. Notice the clear pattern. As x gets larger and larger, the value of 1 over x gets smaller and smaller. Each time we multiply x by 10, the fraction becomes 10 times smaller. Now let's visualize this behavior with a graph. We'll plot the function y equals 1 over x to see how it approaches 0 as x increases. Here's the graph of y equals 1 over x. Notice how the curve starts high when x is small, but rapidly decreases as x gets larger. The curve gets closer and closer to the x-axis, but never actually touches it. Let's mark some specific points on this curve. At x equals 1, y equals 1. At x equals 2, y equals 0.5. At x equals 4, y equals 0.25. At x equals 8, y equals 0.125. The x-axis, where y equals 0, is called a horizontal asymptote. The curve approaches this line but never reaches it. No matter how large x becomes, 1 over x will always be positive, just getting smaller and smaller. The mathematical reasoning behind this limit is straightforward. As x increases without bound, meaning it gets arbitrarily large, 1 over x decreases without bound toward 0. More formally, for any small positive number epsilon, we can always find a sufficiently large number m such that whenever x is greater than m, 1 over x will be smaller than epsilon. This is the precise definition of what it means for the limit to equal 0. Here's a concrete example. If we want 1 over x to be smaller than 0.001, we simply need x to be greater than 1000. This demonstrates that no matter how small we want 1 over x to be, we can always find a sufficiently large value of x to achieve it. Therefore, we have rigorously demonstrated that the limit of 1 over x as x approaches infinity equals 0. This fundamental example illustrates the basic principle behind all power at infinity limits. Now we'll examine our second example, the limit of 1 over x squared as x approaches infinity. This case demonstrates how increasing the exponent dramatically affects the rate of convergence. Let's start by examining what happens to 1 over x squared as we substitute increasingly large values of x. We'll use the same x values as before, 1, 10, 100, and 1000. When x equals 1, we calculate x squared, which gives us 1 squared equals 1. Then 1 divided by 1 equals 1. When x equals 10, we calculate 10 squared, which gives us 100. Then 1 divided by 100 equals 0.01. Notice this is already much smaller than our previous result. When x equals 100, we calculate 100 squared, which gives us 10,000. Then 1 divided by 10,000 equals 0.0001. The value is getting very small very quickly. Finally, when x equals 1000, we calculate 1000 squared, which gives us 1,000,000. Then 1 divided by 1,000,000 equals 0.000001. This demonstrates the rapid convergence to 0. Now let's compare this with our previous example, where n equals 1. Notice how much faster the values approach 0 when we square x in the denominator. The key insight is that squaring x in the denominator makes the denominator grow much more rapidly. When x increases by a factor of 10, x squared increases by a factor of 100. This causes the fraction to decrease much more quickly. This quadratic relationship appears frequently in physics, particularly in gravitational fields. Newton's law of universal gravitation states that gravitational force is inversely proportional to the square of the distance between objects. In summary, when n equals 2, the limit of 1 over x squared as x approaches infinity equals 0, but the convergence is much more rapid than when n equals 1. This quadratic relationship is fundamental in many areas of physics and engineering. Now that we understand the mathematical foundation of the power at infinity limit, we can explore how this concept appears everywhere in the physical world around us. The principle that 1 over x to the n approaches 0 as x approaches infinity is not just abstract mathematics. It governs fundamental laws of physics and engineering. Our first application comes from Newton's law of universal gravitation. This fundamental law states that the gravitational force between two objects is proportional to 1 over r squared, where r is the distance between them. Notice that the force depends on 1 over r squared. This means as the distance r increases, the gravitational force decreases rapidly. When r approaches infinity, the force approaches 0, following our power at infinity limit. To see this in action, imagine placing identical objects at increasing distances from Earth. At distance r equals 1, we have some force F. At distance r equals 2, the force becomes F divided by 4. At distance r equals 3, it becomes F divided by 9. At distance r equals 4, it becomes F divided by 16. As we can see, the force decreases dramatically with distance. This is the power at infinity limit in action. As distance approaches infinity, gravitational force approaches zero. Now let's examine another physics application that follows the same mathematical principle. Electromagnetic radiation, including light, radio waves, and X-rays, also follows an inverse square law. The intensity of radiation is equal to power divided by 4 pi r squared, where r is the distance from the source. Imagine a point source of light. As the electromagnetic radiation spreads out in all directions, it must cover increasingly larger spherical surfaces. Since the total power remains constant, the intensity at any point decreases as 1 over r squared. Again, we see the same pattern. As distance increases, intensity decreases following 1 over r squared. At infinite distance, the intensity approaches zero, demonstrating our power at infinity limit. Now let's see how engineers use this same principle in telecommunications. In telecommunications, signal strength follows a similar pattern. The received signal strength is proportional to transmitted power divided by distance to the n power, where n is typically between 2 and 4, depending on environmental conditions. Consider a cell phone tower transmitting signals. Close to the tower, signal strength is strong. As we move away, the signal becomes progressively weaker following the power law decay. Engineers use this relationship to calculate coverage areas and determine optimal tower placement. As distance approaches infinity, signal strength approaches zero, following our fundamental limit principle. Let's now see how all these applications connect to our mathematical principle. All three applications share the same fundamental mathematical structure. Gravitational force is proportional to 1 over r squared. Radiation intensity is proportional to 1 over r squared. Signal strength is proportional to 1 over d to the n power. They all follow the same mathematical principle we studied. The limit of 1 over x to the n as x approaches infinity equals 0. This demonstrates the incredible power of mathematics to describe and predict natural phenomena across completely different fields of science and engineering. Understanding this connection helps us see that mathematics is not just abstract theory, but a powerful tool that reveals the underlying patterns governing our physical world. We've reached the end of our exploration of the power at infinity limit. This fundamental concept in calculus has taken us through mathematical theory, practical examples, and real-world applications. Throughout this video, we've discovered 3 key insights about this limit. First, as x approaches infinity, 1 over x to the n always approaches 0 when n is positive. Second, we learned that larger values of the exponent n create much faster convergence to 0. The difference between n equals 1 and n equals 2 is dramatic. Third, this mathematical concept isn't just theoretical. It appears everywhere in physics and engineering, from gravitational fields to signal processing. Here's a visual reminder of how the exponent n affects convergence speed. With n equals 1, convergence is relatively slow. With n equals 2, it's much faster. And with n equals 3, it's even more rapid. The applications we explored span multiple fields. In physics, this limit governs how forces weaken with distance. In engineering, it helps us understand signal decay and optimization algorithms. In pure mathematics, it's fundamental to understanding series convergence. If this video helped you understand the power at infinity limit, please give it a like. Your support helps us create more educational content like this. Don't forget to subscribe and ring the notification bell so you never miss our latest calculus tutorials and mathematical explanations. Finally, leave a comment below with any questions about limits or suggest topics you'd like us to cover in future videos. Your engagement helps us understand what content serves you best. Remember, mastering the concept that the limit of 1 over x to the n equals 0 as x approaches infinity is a stepping stone to more advanced calculus topics. Keep practicing, stay curious, and we'll see you in the next video.